Welcome to the solutions to the circular and planetary motion problem set, problems 10 and 11. Number 10, an air puck of mass 0.25 kilograms is tied to a string and allowed to revolve in a circle of radius 1.0 meters on a frictionless horizontal table. The other end of the string passes through the hole in the center of the table, and a mass of 1 kilogram is tied to it as shown in the diagram below. The suspended mass remains in equilibrium while the puck on the tabletop revolves. We need the tension in the string. What is the horizontal force acting on the puck? And what is the speed of the puck? Of course, that would be V. Let's start with a free body diagram of the forces acting on both the puck and the block that's hanging in this problem. Let's start with the block. That seems pretty simple. We have the weight down, and we have the tension up in the string. The string then comes up, passes through the hole, and we have the puck revolving in a circle on the flat frictionless table. The puck would have forces also mg down, normal force up, and the tension of the string towards the center of the circular path. Let's go ahead and answer A. What is the tension in the string? All we would need to do in this problem is summate forces for the block. The block is in equilibrium, meaning it's not accelerating, so the summation of forces acting on the block is 0. That means the tension is equal to the weight. The mass of the block is 1 kilogram times 9.8 is 9.8 newtons. Our next question, B, what is the horizontal force acting on the block? Well, we can see from our free body diagram there's only one horizontal force acting on the puck, and that horizontal force is the tension, which is what we just calculated in A. So that tension is 9.8 newtons, and our answer to B. C, what is the speed of the puck? This tension is what causes the mass, the puck itself, to centripetally accelerate. So we set up a Newton's second law for the puck, sigma F equals ma. Is the puck accelerating? Yes, because it's traveling in a circle. So we put the subscript C on our A. The tension is what causes the mass to centripetally accelerate, which is equal to V squared over R. So T equals mv squared over R. We substitute. We know that our tension is 9.8. We're told the mass of the puck was 0.25. We're looking for its speed, which is squared, divided by the radius of the circular path, which was 1 meter. We go ahead and solve for the velocity, and we should get 6.3 meters per second. All right, on to number 11. Tarzan, mass equals 85 kilograms, tries to cross a river by swinging from a 10-meter long vine. His speed at the bottom of the swing as he just clears the water is 8 meters per second. Tarzan doesn't know that the vine has a braking strength of 1,000 newtons. Does he make it safely across the river? Justify your answer. Well, here's a picture of Tarzan swinging on a vine, and I've added a circular path that he's following in this problem. And what we're going to do is we're going to start by a free body diagram for him at the bottom of the swing, just as he clears the water, where the information is provided for us. What are the forces acting on Tarzan? Well, we have his weight down, mg, and we have tension in the vine up. And we're reminded that this dot representing the center of the circular path, that the center of the circular path is positive. We set up a Newton's second law, sigma F equals ma. Is Tarzan accelerating? Yes, because he's traveling in a vertical circular path. So we put the C, subscript C on our A. And now we summate the forces causing Tarzan to centripetally accelerate. Since the center of the circular path is positive, the tension would be positive and the weight negative, so T minus mg equals mv squared over r. We can go ahead and add mg to the other side and then substitute. And T would be his mass, 85 times 8 squared, over the length of the vine, 10, which is the radius of the circular path, plus 85 times 9.8. We're going to pause here a moment to see if this problem makes sense to us, that the tension in a vine would not only need to supply enough force to support his weight, but it also needs to supply enough force to keep him traveling in the circular path. So it makes sense that we would add the centripetal force and the weight to get the total tension needed by the vine. We go ahead and solve for the total tension in the vine, and we get 1,400 newtons, which is greater than 1,000 newtons, so the vine is going to break. And if it's filled with woman-eating crocodiles or man-eating crocodiles, like our last Tarzan problem, Tarzan is going to die. All right, that's it for 10 and 11. And in class tomorrow, you'll be solving for the solutions to problem number 12.